Hello and welcome to the premiere of the Hour of Scour show. This is our first episode, and before we start with our presenters and hosts, I would like to introduce myself. My name is Christina Scott. I am the technical manager at the Geo-Institute. If you guys know, the Geo-Institute is part of the American Society of Civil Engineers. We are over 12,000 geotechnical engineers and geologists members. And on this show, we have our sorry, we have Professor Stacy Collasia from the Texas State University. She is an associate professor and director of the Create University Transportation Center. To know more about us, about the Geo-Institute, please go to the geoinstitute.org. We also have the Student Participation Fund. In 2024, Dr. John Briaud funded $1 million to the American Society of Civil Engineers, and we create the Briaud Student Fund. If you want to know more about that, please check out in our website. Sorry for that. Stacy, if you are ready, the floor is yours.
Sure. Thank you, Christina. I am Stacy Collasia, and yes, I am the director of the Create University Transportation Center and host of the Hour of Scour. A little bit about why I'm potentially the host. Specific to our UTC, we are a coastal infrastructure durability center sponsored by the US DOT. And if you think about it, coastal infrastructure durability has unique challenges that sometimes our inland infrastructure does not have. And a lot of these are really relevant hazards due to erosion. From storm events, from tidal flooding, from sea level rises, these can all cause issues and with our infrastructure or even undermine our infrastructure. So we have a lot of projects going on, including some of my own related to scour and erosion. And potentially that's how I landed myself as the host of this show. And potentially a little bit, we may talk about how I got myself into erosion work. But for now, I will lead us to the main event and introduce Dr. Jean-Louis Briaud, the man, the myth, the legend of Scour, and our first guest on the Hour of Scour. So, Dr. Briaud.
Thank you, Stacy. Well, first, I want to pay tribute to the Geo-Institute, Brad Keeler, Christina, and many others for all their innovations in the world of online support and stuff. It's been really a revolution. And Brad, you've done a remarkable job, so thank you for that. And then I want to say something about Stacy. Stacy was one of my PhD students, and she was definitely Miss Energy. Now Mrs. Energy. I guess you can tell when when you just look at her on the screen. So much energy, and she worked on finding a way to propagate electricity through the soil and infer the depth of erosion that could take place around bridge supports. So you can imagine mixing electricity and water is not exactly something that people would want to do. And she found a way to do it. And so remarkable work. Thank you, Stacy. All right, so we're going to talk about bridge scour. Let me see if I can share my screen here and all this fancy footwork. Hour of Scour. Here we are. You all see that?
That is perfect.
All right, and then I need a pointer. So boom, there's a pointer. Look at this. Wow. All right, so bridge scour is when bridges are over water, and about 85% of all our bridges are over water in the United States. Then the flowing water erodes the soil at the bottom of the river around obstacles. And we identified three components of this bridge scour Around the abutments here, you see you have a hole that forms. That's the abutment scour depth. And then at the piers, you have a hole that forms because the water has to accelerate around the pier, and that creates a hole. And then across the entire river, you have what is called contraction scour. So these are components that must be considered as part of the design. So here is some, I've got some few photos and movies, and then we can start the question. So here is you see the person standing right here. This is a pier scour hole right here. This is an old photo, but you see the ground surface used to be here, and now it's there right across the entire. So this is contraction scour. I don't have a good abutment scour thing, but you see some problems, and this is the number one cause of bridge collapse in the country. 60% of the time. This is a bridge in Portugal. So we do have a problem in our country, but other countries also have a problem. As I said, this is in Portugal. This is in Japan, Tokyo. 1, 2, bye-bye. The pier is gone. By the way, the bridge is still standing. The bridge deck is probably hanging onto the guardrail, but so it's a problem everywhere. Here's a movie. Wanted to show you this movie. If you look at it, when I do the pointer, I cannot do the movie. How do I get rid of this pointer now? Pointer options, laser pointer, no, arrow options. I don't want any options. Okay, well, somehow, let me try this, enter. There we go. So you see that car is coming to and it looks like something is really happening right here, and you're going to see the bridge collapse. So that car was that close to ending up in the river, and some serious problems. If I move on to the next one, this is, the first one was in Korea. This one is in New York State. A bridge collapsed in 1987. This is the collapse of the second bridge deck. 10 people died, and that really was the impetus to pay a lot more attention to bridge scour in our country, and was corresponding, and a few years later, the development of the first guidance for bridge scour and mitigation. This is a culvert. I don't, let's see. Yeah, you can see here the culvert is under the embankment. It's too small, and this tree is actually sucked into the culvert to go under the embankment. We call this pressure scour, but I don't know if here's another example of pressure scour. This is in Texas, and you're going to see the bridge is going to break, and the bridge is going to actually disappear down the river. The bridge deck, you can see it's gone, and so this is a serious problem. And other areas of erosion, meander migration, for example. This is a 30-year accelerated movement of a river in Peru. And when you see this, you say, my goodness, where in the heck am I going to put the bridge? Because it's moving quite fast. So we have meander problems. This is another, so the river, you're going to see this building is going to collapse into the river. The water is accelerating around the bend, and the building is being undermined and ending up collapsing. This is in Barbuda during a hurricane. Let's see if I have, this is a levee overtopping. In this case, the water doesn't overtop the levee, the waves do. And you can see that the waves on the downstream side of the levee eroding the material. This is this is northern Germany, 1954, and we've made quite a bit of progress since then, fortunately. But if you can see, the erosion is starting right at this point right there, and increasing, and then there's a point where the levee simply is breached, and you have dramatic flooding inward. And in nature, we find a number of cases where erosion is prominent. Lake Ontario is right here, boundary between the US and Canada. And it turns out that Lake Erie is higher than Lake Ontario by about 50 meters. And so the Nagara Falls goes from Lake Erie to Lake Ontario. And 12,000 years ago, the Nagara Falls were at the Lake Ontario location. And since then, by retroactive erosion, they have moved backward to about halfway now between Lake Ontario and Lake Erie. You see them on the left here, and the Canadian Falls were here in 1841. They're now in 2006. So the regression is about 11 kilometers of land erosion from Lake Ontario to Lake Erie in 12,000 years at about 0.1 millimeter per hour. One more. Grand Canyon, that's a big hole in the ground. Now, I remember the first time I went to Grand Canyon, I kept driving up and up and up and up. I said, my goodness, this is a mountain. And indeed, it's a mountain, because at the bottom you have the Colorado River that has to be at positive elevation so it can go drain in the ocean. And so how is it possible for the river, the Colorado River, to face a mountain and then decide to cut it in half and dig that big hole in the ground? So that's my first question to the audience. How is it possible for the river to have made such a big hole in the Grand Canyon? Now, obviously, this took place in about 10 million years. So the rate you see it here, 0.00016 millimeter per hour. And if you look at this number, you say, oh, that's negligible. And if you neglect this, you essentially neglect the Grand Canyon. So yeah, question, how's that possible? One more, a question for Stacy. If your faucet drips on a pebble for 20 million years, will there be a hole in the pebble? And actually, I don't know the answer, so there's no wrong answer in this one, Stacy. But we've been working in this erosion stuff for 35 years, including bridge scour, meander migration, levee overtopping, cliff erosion, internal erosion of dams. And it's required developing tests to measure the erodibility of a soil on a site-specific basis and develop prediction method to estimate the erosion extent. So I'll stop here, and I'll send it back to Stacy for questions and Christina.
Cool. Well, thank you. I think you covered initially, I thought maybe we should define scour, but on this slide, maybe a little bit different. So, our scour, how is scour different than erosion? If you say I work in erosion or I work in scour?
Well, we typically use the word scour for bridge scour, erosion of soil around bridge supports. So I would call bridge scour, but meander migration, that I wouldn't use scour. I would use erosion, levee overtopping erosion, cliff, internal erosion of dams. So the only time we use scour is for bridge scour.
Which one is your passion? Do you like one more than the other, general erosion, or are you more into the specific scour challenge?
The erosion of soils and rocks in general is fascinating. It really has brought me to think in a totally different scale of size, because when we deal with foundation, retaining wall, slope stability, we're talking about meters, tens of meters in size. But when we work in erosion, we have to think at the particle level. And as you know, we're talking about 0.00 millimeter, 0.01 millimeter. I mean, it's a totally different scale. And scale of time as well. You saw the Grand Canyon. We have to think sometime in geologic time rather than lifetime or design lifetimes. So it's fascinating in all of them. And bridge scour is probably what I've worked most.
I gotcha. So bridge scour, I guess specifically, is traditionally a hydraulic problem. What do you say to the hydraulic engineers that say that this is my challenge to solve? Go away, Mr. Geotech.
I faced that question in 1990 when I first got involved. The hydraulic engineers were fairly protective of their domain. And I would say now the geotechnical engineers are starting to realize that they should be involved, and so do the hydraulic engineers. So I think, it's clear it's an interaction, and the water does the loading, and the soil does the resistance. Incidentally, if you think of civil engineering in general, the engineer who knows about the resistance is typically the one that designs the project. For example, if you have wind load on the structure, the wind engineer is not the one that designed the structure. If you have and it's reversed if you know the foundation design is the geotech person that designed the foundation that gives the pressure that you can put on the foundation. The structural engineer gives you the load, but it's the geotech. So in a way, in the scour business, it's inverted. The hydraulic engineer is the one, the water is generating the load, the soil is the resistance, but it's the loading engineer that does the decision process. So it's a different story, but it should be a 50-50.
Both working together.
Absolutely. Even the structural engineer involved in that.
Sure. I'll give the friendly reminder, and then I'll throw to Christina that if anyone has any questions, please don't hesitate to put them in the chat, and Christina or I will ask Dr. Briaud, or me. I guess you could ask me a question if you're in the mood. We're happy to answer any. Sorry, I cut you off there, Christina. Did you have a question?
Yeah, so thanks for the reminder, Stacy, and thanks for this introduction, Dr. Briaud. So I have a quick question. Again, scour is not my expertise. So when you talk about bridges, I think it's amazing how deep we need to go to install a pier or, start the construction. So how deep we need to go to get good ground?
Well, one of the films that I showed, the videos that I showed were a bridge where the pier was on shallow foundation. So it's a few feet into the ground, all the way to big bridges now that have, 100 meter, like almost 300 feet deep piles. So geotechnical engineering in general is 0 to 100 meters in depth. Much below that is petroleum engineering, and much shallower than this is agricultural engineering. But the geotech folks work 0 to 100 roughly.
So you said in the 90s you got pushback from the hydraulic engineers. How did you get into scour? Was your doctoral research related to scour, or is it a challenge you saw, or what are we talking here?
No, not at all. It came because, as you know, Stacy, and the professors that are online, we're in a business where, like everywhere else, there is competition, and it made sense to me to try to renew myself in different topics every 10 years or so. So for the first 10 years of my career at Texas A&M University, I worked with in situ testing. And then in 1990, I attended a conference, and somebody was talking about Scour. I said, man, that sounds really interesting stuff. And then I started to dig, and I saw that hydraulics. I said, wait a minute, no geotech in this thing? That's my call. So I decided to get involved in geotech because I saw the opening. I said, surely there is room for me to work in this area because I don't see much geotech contributions prior to that. So I got involved. And the first thing, it's amazing, within civil engineering, the fields are quite different. You know, in hydraulics, they have nice computers and the color screens and stuff. You know, geotech, we have this as well, but the other part is our reflex is to go to the site, collect a sample, bring it back to the lab, test it, and say, okay, it's going to be strong, it's going to be weak, or it's going to do that to this. And so that was my reflex. I said, okay, I got to go get some samples and develop a machine that will tell me how erodible the material is. And that's how I started, you know, by developing this erosion function apparatus that you know well, Stacy. And people started to say, oh, well, you know, that makes sense to, but there was quite a bit of pushback because hydraulic engineers are not the type that say, okay, we're going to take a sample of water and we're going to test it. You know, to them, water is water is water. And for us, soil is not soil is not soil. So we have to make the distinction between one side or another. And so that's how I started to publish and started to talk, and people got me involved in their projects. And so it grew from there. And really, again, if you're a geotech, there is money, there is interest, there is work to be done, continue to be done. You know, not everything has been solved. So, Stacy, you haven't answered the pebble stuff.
Oh, yeah, my pebble thought. Oh, I would say in a traditional geotechnical fashion that I think it depends. On one hand, if your rock is relatively soft and erodible, rocks can be relatively soft as maybe even an intermediate geomaterial, I think you would have no rock. If it was behind my house, where our water is so hard here that I bet in 20 million years you would have more like a stalagmite where it's built up the water deposit and has actually plugged the faucet, which is good because water is expensive, and then I wouldn't be dripping anymore. And so I lean towards my own experience. I think that's what I would have, a stalagmite to the faucet.
Christina, what do you think?
I am a geologist, so I know a little bit about the hardness of the rock. So I think if we have a lot of mica or that kind of rock, it's going to disappear. Like nothing is going to be suitable. So yeah, those are my 2 cents. However,
Go ahead.
I'm sorry. So we have some questions. So if we want to like go into them, we have some questions in the chat. The first one is from Cassie Rutherford. Can you talk about how climate change will impact erosion and scour? That's the first question.
Absolutely. Let me see. Stop sharing. How do I do that? Stop sharing. Here we go. Stop sharing. Thank you, Cassie. Well, it's going to impact hydrology. It is impacting hydrology. And hydrology has a big impact on scour and erosion in general, because even if you consider only the 100-year flood, then that's going to change significantly. And every year, you know, by the way, in hydrology, when you define the 100-year flood, you got to do flood frequency analysis, and then you find your probability corresponding to 100-year recurrence interval. And the scatter in hydrology is remarkable. I mean, as a geotech, when I look at the scatter in doing you know, predicted versus measured scatter plots, In structures, you see a nice line like this. You say, oh my goodness, these guys are good. And then you look at geotech and you say, oh my goodness, we're not quite as precise. And then, so we tend to put our scatter on log-log plots, and suddenly, boom, it reduces and we feel good. Well, I tell you what, in hydrology, when you look at predicted versus measured, it makes me feel good. It makes any geotechnical engineer feel good because the scatter is dramatic. I mean, anyway, so it's a tough field, but that's going to impact the 100-year flood. And then you wonder what flood you should be considering for designing a bridge. Because I can tell you, if you do the calculations, the 100-year flood has over 50% chance of occurring in the design life of a bridge. We design bridges for 75 years. And during those 75 years, the chance you're going to get the 100-year flood is over 50%. You say, oh yeah, but then we consider the 500-year flood. All right. For the 500-year flood, the probability that you're going to get it during 75 years is 15%. That's still not acceptable in my mind. That's way too high. LRFD, we designed for 1 in 1,000, typically on columns, beams, elements, foundation elements. And so if you want to meet a probability of 0.1%, which corresponds to an RFD, you need to go to the 100,000-year flood. And of course, when I say that, people say, go home, Briaud, we don't want to hear that.
Who's going to pay for it?
Well, no, but the thing is, it's a highly nonlinear process. 500-year flood is 5 times larger than the 100-year flood. No, because when you go from the recurrence interval to the flow, to the velocity, to the scour depth, all this is multiplied to the power much lower than 1. So the scour depth may be the recurrence interval, if you want to do it that way, to the power 0.1. So now you have 500 divided by 100, 5 to the power 0.1. So let me do that. 5 to the power 0.1. Boom. 1.17. So if I go from the 100-year flood to the 500-year flood, I increase the scour depth by about 20%. And for 20% increase in scour depth, you buy yourself a significant increase, a decrease in probability of occurrence. So we need to think about this. I mean, you got me started, Cassie. I was president of ASCE, and that opened my mind to civil engineering in general. So I had to deal with hydraulics, with geotech, with structures, with environmental, transportation. And I can assure you that we do not operate at the same risk level in all of those. And we need a project that looks at the risk involved in each one of those subfields of civil engineering, even out the risk. And now we have a very good target, a very good basis to make decisions in our projects. Anyway, yes, the answer is yes. It will have an impact.
The short answer.
Short answer.
So another question that's kind of close to something that we've done. Chelsea Brummer asked, scour predictions and intermediate geomaterials like mudstones, siltstones seem to be highly over-predicted. Is there research or guidance being developed to help refine bridge scour estimates in these materials?
Oh, geez. Hey, you're sending all the good questions. They're all the tough ones. Yeah, it's a very difficult material. Yes, you're right. So we have the soils and we have the rocks. And in between, we have the intermediate geomaterials, IGMs. And these IGMs vary quite a bit. I mean, the big problem in rock mechanics, and including IGM, is the difference between the intact IGM core behavior and the behavior of the mass. So, and that includes erosion, because erosion is at a scale I was talking about, these mini scales because you think of the grains that have to be eroded. But the bridge pier may be 10 meters in diameter. So now you're talking about a large area that the water is eroding. So at that scale, you have a fissured rock mass. And the question is, how will the rock erode? Well, you have, or IGM, let's see, I'm a parenthesis. IGM is between soil and rock, okay? That creates a problem in itself because in soils, we have consolidation. In rocks, we have mostly elasticity. In soils, we have more Coulomb. In rocks, we have the hook strength envelope thing. So when you come to the boundary, you really have a discontinuity of fields, and that creates a big problem for IGM. So when you look at IGM, you say, okay, if I consider it to be a rock, I'm going to do this. If I consider it to be a hard soil, I'm going to do something different. Close the parenthesis. And now I forget what I was saying. That's all right. So anyway, it's a tough problem. One of the things that's important, I think, for IGM is the distance between fissures, because that probably will create a faster erosion process than the erosion itself of the intact material between fissures. And let me show you something here. I'm going to take a piece of paper and I'm going to try to do an experiment. So I don't know if everybody sees this, but so here is the experiment. I have a piece of paper here, and this is the particle or the rock block. If I blow from underneath, obviously the sheet of paper goes up. But if I blow from above it, you can see that the sheet of paper also goes up because I create a decrease in pressure. There is a vacuum that takes place because the air has to accelerate. And so there is an upward motion that is generated on top of the particle. So the erosion process is not just a drag, but it's also a plucking upward. And in our current models, we don't have this uplift component. We only reason in terms of shear stress and drag force. And so when it comes to rock scour and IGM, fissured IGM, I think the plucking is going to dominate. And I would say if I had a problem, an erosion problem in rock right now, I would look at the distance between fissures, and I would use that as a D50, the diameter 50% passing, D50. And I would look at the critical velocity on the relationship between critical velocity and D50. And I would take that as the critical velocity of the IGM. But yeah, we have a big project with the Texas DOT right now to look at IGM erosion because, as you said, the predictions tend to be very conservative, and we can't afford to be that conservative with infrastructure construction because we're in deficit and we need to be much closer to reality.
Yeah. That's a good point. We just finished some work for the Kansas Department of Transportation, and it was for shale specifically on cut slopes. And they exposed these back slopes and intact shale. Fine. And they give me a sample and I test it. It doesn't erode. I mean, like some of the samples we have, we couldn't even get it to get out of the Shelby tube. 5 grad students hanging on the edge of something trying to extrude it like this. Madness. Can't get it out. Some of them we were able to get out. A few of them we got to erode. But the reason we got the project is because over time, Kansas has very extreme freeze-thaw temperatures, and water gets in those fissures, and it turns to what I very technically and eloquently called fluff. And this material, it goes on the surface, I mean, I put it in a machine, away it goes. I fill the machine with water, away it goes. And so the point of the project was kind of to show, okay, you could say that it's not going to erode, and that's true, until it turns into the fluff. And then it becomes super erodible. And this is a huge asset management problem for the DOT, because they have to maintain this material that's now quickly eroding from the site. And how do we predict this weathering process? And it's not trivial, and it's not trivial to predict the change in erosion. It's not trivial to predict the change in weathering. It's more of a geology question for Christina. Maybe I should have called her up. But it was wild, the difference in the exact same soil sample that we would get from, like, in the same Shelby tube within 1 foot. Fluff, can't erode, all in the same zone.
Yeah. Well, there's another, and the slake durability test is quite helpful along those lines. But the other thought is, if you have a river that's always full of water, but in Texas, for example, we have rivers that are ephemeral. So they're wet in the spring and they're dry in the summer. And if you have a bottom that's shale, for example, then it's wet and the fissures close in the spring, and in the summer it opens up to the sun, it cracks up, and you've got a few inches that become totally loose, and then the first flood, and it cleans up that loose material from the top of the shale. So it can get to be complex for sure.
For sure. We have kind of a related question to these in terms of just predicting what's going to happen. This is a fun one. What are the most uncertain factors in predicting and Scour prediction modeling?
Oof. Well, I mean, the erodibility of the material. I mean, when we do. So we do, like others, do simulations. So the simulations have the water part and the soil part. The computational fluid dynamics, very well developed. There's a bunch of programs available, Star CCM, Flow 3D, ANSYS, Fluent, you name it, all kinds of solutions. On the soil side, that's where it becomes very tough. And you can either do mesh morphing or discrete element method solutions, but that is the largest uncertainty. One hydraulic engineer one time who seemed to not like the idea of testing the soil said, well, you're testing only in these 2 points, and the pier has a lot more soil around it, so you don't know what's happening in the other area. I said, well, at least I'm testing 2 points. It's better than what we were doing before, where we didn't test anything at all. So yeah, definitely the soil erodibility to me is the most difficult part, and we developed this method called the observation method, and I remember after about 10 years of working on the EFA and trying to determine the erodibility of a material on a site-specific basis with this instrument, we developed a new technique, and we hoped that we had improved significantly, and we used a large database that the USGS had generated, and we compared before and after. Before we did our work, and then after, as we had done our work. No improvement whatsoever. The frustration was at its highest point. I was frustrated. The students were they were down on themselves, and at that point I said, all right, we just spent 10 years of our life, and we haven't improved at all the process. And I said, I've got to think very differently. And then, you go in the backyard and you rest a little bit and look at the sky and say, what would Terzaghi do? Or what would Peck do? And then after a couple of beers, I thought, well, observation. Terzaghi and Peck were really big on observation. And so the observation method is something that we learn in school, in geotech school, and we kind of accept it. And so that's when the observation method was originated. And we say, well, we'll go to the site, we'll see how big the hole is, we'll find out the biggest flood that this bridge has seen, and we'll use those 2 calibration points to extend it to the 500-year flood or the flood that we might be worried about. And then we were able to, fast forward another 10 years, and now we were able to show much, much better correspondence between predicted and measured, much, much improved. So we felt good. But after those first 10 years, depression, let me tell you.
Did the students graduate? Or are they still there? They had to wait the 10 years?
Yeah, no, they did graduate. Or they had made a contribution to new knowledge. Suddenly in the equation, there was a soil parameter. That was big time, but it didn't work. And the articles were published, and I never had the courage to say, don't use this, it doesn't work in a future article. Sometimes we should do that. Now I can do that because I don't care.
That's funny. I had I got to meet Professor Schmertman one time. There's a picture, he was in Florida. And there's a picture of me standing proudly next to him to show my students, look what I'm doing. And I said, I teach the Schmertman method in foundation design. And he was like, oh. On his face, I was like, do we not believe? It's in the manual. Is it okay? And he was like, I thought, that's interesting. So maybe you can just start making the face when people say they're using your methods.
Stacy, you want me to take the next question?
Yeah, sure. I'll say.
Okay, great. This one is from Aliriza. Could you please discuss the scour in urban areas caused by flooding and hurricanes?
Describe the scour in what?
In urban areas.
Urban areas. I guess he's referring to levees. I guess. Yeah, this is a big topic, and I got involved, I guess, in 2005 during Hurricane Katrina. We went to different sites around New Orleans, got some samples. Were you there at that time, Stacy? Maybe Michelle.
No, I was a freshman. No, we did the Midwest levees.
Yes, that's right, the Midwest levees. That was that was another case. So one big difference with levees, hurricanes may overtop the levee for, let's say, 2 hours. But rivers can overtop a levee for 2 days. So there's a significant difference between a hurricane and a flood, a river flood, in terms of the amount of time that the levee is going to be loaded. But one of the issues around New Orleans, and I think in the country in general, is that levees have been built over the last 300 years. And we don't know what they're made of. I mean, when we went around New Orleans and collected some samples, we tested them in the EFA, and we got a scatter like you wouldn't believe. We had anywhere from fine sand all the way to high plasticity over-consolidated clays, and everything in between. So and of course, we knew which levees had been overtopped and failed and were breached because there was evidence, like big ships on top of the levee. So that was clearly evidence of overtopping, and I've got some slides, but and some levees had been overtopped but had not been breached. So we used the chart that we developed, this erodibility chart and categories, to say if you have a soil in this zone, it's gonna be able to resist a hurricane, a 2-hour overtopping. If it's in this zone, nothing's gonna resist. It's gonna be obliterated. And then essentially, because soils cannot take more than about 4 meters per second of velocity, of water velocity. Anything about 4 meters per second, forget it, the soil is gone. Clay, you name it. So now, when we go to rock and riprap, it's a different story. But soils, 4 meters, top limit. Now, grass, if you put grass on top of the soil, you probably can, not all grass, but if you do it right, you probably can go to 6 or 7 meters per second. Okay, so the grass improves the resistance by about 1 erosion category. But overall, we have a big project right now to look at mitigation of levee overtopping. And so we're trying different things, chemical additives, geosynthetics, to try to find things that are, because there's 10,000 miles of levees in the country? So if you want to fix it, and to me, the goal as a civil engineer to try to take care of the public is to minimize the probability of failure. We cannot bring that probability of failure to zero. It's not possible. Failures have happened. Failures will continue to happen. We don't like it. We aim for 0 failures, but we have to accept the fact that things are going to fall down. And we don't convey that correctly to the public. Some people behind the levees say, oh, I'm behind the levees, no problem. That's not right. The levee, there's a limit to the levee, and we need to convey that that message to the public. I think it's pretty important. And then a levee is a single chain. You break any part of that chain, you break the whole chain, you break the whole system. So to me, that's where we have to think in terms of redundancy. We have to have a second line of defense. When they talk about polders and that makes a lot of sense. But we cannot rely on a single unit of defense to be able to increase dramatically the probability, decrease dramatically the probability of failure. I mean, you know that, Stacy. When you have 2 systems, if they're independent, and one is at 1%, the other one is at 1%, then both of them are 10 to minus 4. Because you multiply the probabilities. And so trying to harden a levee line, you probably can get your money to go a lot further if you think of redundancy. Yeah,
I agree. And I think I remember you had a student there. I got to go when Hurricane Harvey hit Houston and go to see kind of the damage that was done there by the flooding. And in general, Houston did quite well. We saw a lot of bridges with huge scour dishes, fish that would die that were now inside the scour dish that were no longer in the river as it retreated. Some panels had been uplifted on roads that became bathtubs for a while that it was never designed for them to be bathtubs. But it's not the same as water flowing along this long linear system because eventually it came out of Houston.
Well, by the way,
you pick which one to design for, right? I mean, it did well. Houston, Harvey was massive. How was that different than New Orleans?
Well, Harvey, there was a lot of rainfall because when it became a tropical storm, it sat on Houston for a long, long time, and there was a lot of rainfall. And so there was flooding of the city, but I'm not sure there was, like you say, a lot of water flow. Now, by the way, that rainfall reached, I forget where I saw this. It was kind of the 5,000-year flood or 5,000-year rainfall. And you say, okay, 5,100-year flood. My God, this is 50 times larger. No, it's not. Again, because it's nonlinear, and then you have the power exponent, and it really, so don't be scared if somebody says, you need to design for the 10,000-year flood. Calculate what really means in terms of increased velocity and scour depth.
Oh, now I've got some questions. These will be fun because I don't. We'll go for a relative question. What scour countermeasures do you recommend for bridge substructures, and how effective are they? What are you going to put your money on?
Well, the practice right now in our country is to allow protection of the abutment. So allow riprap on the abutment. So usually we don't worry about abutment scour because it's theoretically protected by well-chosen riprap. We don't allow riprap or protection around bridge piers in the river. And the reason for that is going back to 1987 when those 10 people died on Coharie Creek, because there was riprap around that bridge pier. And my Swiss colleagues call it baby riprap, but in Switzerland, when they use riprap, they blow up a mountain, they've got huge blocks, and then now that's serious riprap. Well, I think the riprap size in the US, we think too small. We need to really have some serious riprap size. And incidentally, when you put riprap on the slope, you don't have the same critical velocity. And most of the recommendation come from critical velocity of riprap on flat ground. And so that's another, difficulty. But so back to so that's why we don't allow riprap or protection at bridge piers. Instead, we have to calculate the depth of the scour hole, and then we have to ignore that depth and calculate how much deeper the foundation has to be able to carry the load if you have a 500-year flood that comes through. However, if you get a big hole in the ground after a big flood, then you're allowed to put riprap in the hole as a repair technique, but not as a design technique. So definitely the simplest technique is riprap. If you use riprap, make sure you put a filter between the riprap and the soil, because if you just dump big blocks, the water will find a way to erode the soil between the big riprap. The riprap won't move, but it's going to go down. And so you need, and the geotextile filter fabric is typically the best and the best technique to put between the riprap and the soil. I like articulated concrete mats because they're relatively easy. They have the filter essentially below those concrete blocks, and they're easier to place. So I kind of like those. I haven't checked the cost, riprap versus this. I don't like the hardening, the concrete facing, because these are very rigid layers. And if the erosion takes place at the bottom of an abutment that has a concrete cover, you're going to break the concrete cover and you have a mess, and it's going to dismantle the stuff. Water really does not like joints. Anytime there is a discontinuity, it's there. Oh, I'm going to take care of this one. It managed to make. Look at Oroville, the Oroville Dam. You had a spillway, looked beautiful, beautiful, but there were some joints between the mats. And then the water found a way to get into the joints, lift one of the things, and next you had a mess. So, riprap is by and large the simplest solution.
Yeah, I think we need some new solutions. And I think we need to quit being so reactive, kind of the same way we are in the design. We go for a 100-year flood and we know maybe that's not good enough. This idea that I'm going to calculate the scour and hope that that's enough, and then go back and fill it in with rocks. We should be doing better these days, right? Yeah. Either better at our predictions or be a little bit more, you said, proactive.
Crazy glue. Crazy glue.
Crazy glue.
There you go.
Well, there's a lot of really cool research on different shapes that haven't really taken off of foundation shapes to alter the flow. A lot of research on flow altering strategies that are pretty cool, but getting them to actually be implemented and more cost effective, I think, is still the challenge that we have.
Well, even the shape of the pier. I mean, the piers that we use, when you look at bridges, the shape of the pier, you would never fly an airplane with that kind of shape.
Exactly.
And it's the same problem. The flow, I did the demonstration here using the sheet of paper and air. Well, it's the same as water. And so I would think, but I'm not sure that it makes that big a difference. You do minimize, but maybe 10%. It's not going to make 50% difference, the shape of the pier, but it could make some.
Yet. We have to find the shape, the optimal shape.
There you go. Yeah.
All right, let's go to the wild, wild west of questions. That's what I'm going to call these. Can you talk about the scour power of liquefied soil, like a liquefied mine tailing compared to water? Oof. I have no idea the answer to this one, so this is all you.
Well, I guess the so tailings. I guess you have to have flow to have erosion. So if the tailings are behind a tailing dam and not moving, well, that's good news. But sometimes the dam fails, and you have flow of those tailings. And I guess that brings about the question of sediment transport and the issue of water erosion, clear water erosion, and water laden with fine sand or fine clay particles and you would think that when you have fine sand in the water, you have much more chance for abrasion in the erosion process. We did that in the EFA. And so we had the soil sample, and before the flow was this way, and here we were injecting sand so that the water would be full of sand, full of sand, 10% by volume, something like this, going through. Big problem was the pump didn't like that. The pump didn't like to crunch on sand. And we messed up a $2,000 pump, so we said, all right, no more. I don't know. I am not sure that it's going to make that much difference. The chemistry of the water actually makes a fair amount of difference. For example, if you have an erosion problem offshore, you probably should, and if you want to do the test, you probably should mix a lot of salt to get to whatever it is, 36,000 ppm salt concentration, because that's going to impact the erosion of clays. If you have salt, you have a lot less erosion than if you don't have salt in the water. So water without salt, with very low, like tap water, for example, at 500 ppm or whatever, erodes a lot faster than salt water or seawater. For clays, or for sand, it's not going to matter. So there are a lot of factors like this that can have an impact.
All right. We have more questions, but just to be mindful of everyone's time and end on a high note, and then maybe we can come back to some of these questions. I don't know. I'll leave that to Christina to decide. Here's my last question. What has been your favorite scour project of all time and why? Oh, and you don't have to have done it, but it's probably more fun if you have.
Well, actually, it was the problem of the erosion of the cliffs of Normandy, where the Congressman Chet Edwards in Washington contacted Texas A&M, and there was a problem at Point du Hoc. In 1944, June 6, 1944, when the Allied forces landed, there were a number of beaches, and there was one cliff, Point du Hoc, cliffs that are 100 feet tall, and there's still some monuments that are left from that war, and the cliffs were eroding, and the monuments were about to fall in the water. And it's the land belongs to France, but the area is maintained by the Americans. So the problem was that the cliff was retreating, and basically the problem was that the water was making big caverns at the bottom of those cliffs, so that when the caverns became too deep, then the top of the cliff was falling down. And so the erosion process was pretty simple. We decided to backfill the cliffs and put the monuments on micropiles so that they could reopen the monuments and the visitors could come back and visit that site. By the way, it's kept remarkably well. So if you're ever in that area, this is well worth going to see. But for me, it was very special. You know, born in France, raised, educated, and hearing stories around the dinner table of my grandmother and so on, and being involved in a project that was associated with young people climbing those cliffs to come essentially to deliver my parents. Very special, very special.
That's cool.
All right. Well, thank you so much, Dr. Briaud. Thank you so much, Stacy. This episode is being great. I have been learning so much about Scour. Like, I know the word, but now I know where to apply it. So thank you, everybody, for joining us today in our first episode on the Hour of Scour. I would like to give a few reminders. Next week, we have GeoLegends, May 27 at 2 p.m. We are going to be celebrating Ralph Peck's life. Our moderator will be Marino Dean. And we have the panelists, Gabe Fernandez from the University of Illinois, Bob Gilbert from the University of Texas at Austin, Susan Lacaze, Norwegian Geotechnical Institute, and Tim Stark from the University of Illinois. Please, if you like what you watched today, follow us on our social media, subscribe, like, hit the bell, etc. Thank you, everybody, for joining us today, and see you in the next one.